Imagine you've got a row of books on your shelf that are all mixed up, and you can't pull them out one by one. You can only grab a chunk and flip it around. How many of those flips would it take to get them back in perfect order? That's the heart of sorting by reversal. Given two sequences, we want the smallest number of segment reversals to turn one into the other. Over the next few minutes, we'll unpack what we mean by reversal distance, see why it's not just a neat puzzle, think genome rearrangements in biology, and explore the clever algorithms that find those optimal flips quickly. By the end, you'll not only grasp the theory, but also appreciate how these ideas power real-world problems. Ready to see how flipping chunks can solve big challenges? Let's dive in. Now let's outline the 3 essential criteria for any approximation algorithm. First, feasibility. The algorithm must always produce a valid solution that satisfies the problem's constraints. Second, tractability. It needs to run efficiently, typically in polynomial time. And third, quality. There must be a provable bound showing that the algorithm's solution isn't too far from the true optimum. Together, these requirements ensure our approach is practical, scalable, and delivers reliably good solutions. Isn't it fascinating that despite sharing almost identical gene sequences, turnips and cabbages look and taste worlds apart? On the left, you'll spot a cluster of round, pinkish turnips with their smooth root surfaces and gracefully tapered stems. On the right, compact cabbage heads reveal broad green leaves wrapped tightly in neat concentric layers. This striking visual contrast shows how a single genetic blueprint can be molded into distinct shapes and flavors through variations in gene regulation and development. Building on that contrast, we now have a clear example of a gene order reversal between cabbage and turnip. In cabbage, you see an upstream white region followed by 4 colored gene segments in the sequence pink, green, brown, and then blue. But in turnip, a chromosomal inversion flips that entire block, so those same 4 genes appear in reverse order: blue, brown, green, then pink after the white region. This diagram really drives home that although both species carry the identical genes here, their linear arrangement has been flipped. Such structural variations can have profound effects on gene regulation and ultimately shape the physical traits we observe. Building on the previous slide, this illustration shows a straightforward gene order reversal between 2 related species. Each colored arrow represents a single gene in a linear chromosome segment. At the top, you see the original 5-gene sequence: white, blue, brown, green, and magenta. The curved gold arrows highlight the block that flips during inversion. On the bottom line, after that inversion, the blue and brown genes have reversed orientation relative to their neighbors, even though all 5 genes remain intact. This local reversal event demonstrates how the same set of genes can end up in a different order, and sometimes pointing in the opposite direction, when you compare the turnip genome to cabbage. Building on the previous slide, we now compare a short stretch of DNA from cabbage, top, and turnip, bottom, to illustrate a gene order reversal. In the turnip sequence, 5 genes, white, blue, brown, green, and pink arrows, all point in the same direction. In cabbage, you still see those same 5 genes, but notice how the green arrow flips its orientation relative to its neighbors. The curved arrows highlight this inversion. This simple reversal event reorders the local gene arrangement and clearly distinguishes the cabbage sequence from its turnip counterpart. Building on that example, here we have 2 representations of the same 4 genes in cabbage versus turnip. In cabbage, they line up magenta, green, brown, blue. In turnip, those very genes appear as blue, brown, green, then magenta. Essentially, the middle segment has been flipped. Notice the curved arrow highlighting this reversal event. Our goal is to quantify evolutionary distance by counting how many such reversals separate one genome from another. So the key question becomes, how can we model these reversal steps in a formal way to compute that distance? Building on that reversal event, let's now compare the order of 5 genes in cabbage and turnip. At the top of the slide, the cabbage gene cluster is shown as 5 colored arrows. From left to right, gene 1 in white, then a magenta arrow labeled -5 to indicate gene 5 is inverted, followed by a green arrow for gene 4, a brown arrow labeled -3, showing gene 3 flipped, and finally a blue arrow for gene 2. Below, the turnip cluster displays those same 5 genes in their standard orientation: white for gene 1, blue for gene 2, brown for gene 3, green for gene 4, and magenta for gene 5, numbered 1 through 5. The curved arrow between the diagrams highlights how inversions have reshuffled both gene order and orientation between these two species. This example really underscores how even closely related plants can differ in their genomic layout. Building on that rearrangement example, this slide illustrates 2 linear arrangements of the same 5 genomic blocks and shows how the cabbage ordering can be transformed into the turnip ordering by a series of reversals. At the top, the cabbage line, labeled B. oleracea, reads: Block 1 in the correct orientation, then Block 5 inverted, Block 4 forward, Block 3 inverted, and finally Block 2 forward. Each arrowhead marks the direction of a block. Below, the turnip line, B. Campestris displays the blocks in perfect ascending order: 1 right-pointing arrow, 2 right-pointing arrow, 3 right-pointing arrow, 4 right-pointing arrow, 5, all oriented forward. Key takeaway: those 2 inverted blocks, 5 and 3, in the cabbage arrangement must be flipped and repositioned through reversal operations to sort this permutation into the straightforward turnip sequence. Building on that example, let's watch how the cabbage genome order transforms into the turnip order through a sequence of reversals. On the top line, the cabbage arrangement is represented by the signed permutation: 1 minus 5, 4 minus 3, 2. In the second line, our first reversal flips the segment between positions 2 and 5, yielding MIVE: 1, 5, minus 4, 3, 2. Next, on the third line, a second reversal targets the central segment and produces true: 1, 5, 4, minus 3, minus 2. MIVE. Finally, the bottom line shows the fully sorted sequence: 1, 2, 3, 4, 5. Exactly matching the turnip genome order. This concise series of 3 reversals perfectly illustrates the core of the sorting by reversal problem: finding the shortest set of segment reversals needed to convert one genome's gene order into another's. Building on the previous example, here's how we sort the signed permutation. .pi equals 2, minus 4, minus 3, 5, minus 8, minus 7, minus 6, 1. Into the identity, gamma equals 1, 2, 3, 4, 5, 6, 7, 8. In 5 clear steps. Step 0. Start with new. 2, 4, 3, 5, 8, 7, 6, 1. Step 1. Reverse the segment, minus 4 minus 3, giving do 2, 3, 4, 5, 8, 7, 6, 1. Step 2. Reverse the segment, minus 8, minus 7, minus 6, giving caliber 2, 3, 4, 5, 6, 7, 8, 1. Caliber. Step 3. Reverse the prefix up through the 1, the block 2, 8, flipping its sign on the end to get 2, 3, 4, 5, 6, 7, 8, 1. Step 4. Reverse the entire block, minus 8, minus 1, which produces 1, 2, 3, 4, 5, 6, 7, 8. Step 5. Label the result as gamma equals 1, 2, 3, 4, 5, 6, 7, 8. Each reversal fixes one or more genes into their correct positions and orientations. In just 5 operations, we've transformed pi into the identity permutation. Having just seen how signed reversals work, let's now look at the simpler unsigned case. We start with the identity permutation pi equals 1, 2, 3, 4, 5, 6, 7, 8. First, we apply the unsigned reversal Rho, 3, 5, which flips the block in positions 3 through 5. 3, 4, 5 becomes 5, 4, 3, turning pi into 1, 2, 5, 4, 3, 6, 7, 8. Next, we apply RHO 5, 6, swapping the elements in positions 5 and 6, flipping 3, 6 into 6, 3, and arrive at 1, 2, 5, 4, 6, 3, 7, 8. So there it is. Which version do you think is harder to solve in general, this unsigned case or the signed reversal problem? And which one falls into P versus nitrogen monophosphide complete? Now that we've posed the question, let's answer it. Which version really gives us grief, signed or unsigned? It turns out the unsigned reversal problem is nitrogen monophosphide hard, while the signed case admits a polynomial time solution. Because the unsigned case is the truly challenging one, we'll devote the next sections to developing an approximation algorithm for it. Building on that idea, let's look at the permutation pi equals 1, 2, 3, 6, 4, 5. Notice that the first three elements are already in the correct order, so there's no reason to break them. We call the length of this sorted prefix pi, which in this case equals 3. From this observation, a natural greedy strategy arises. At each step, choose a reversal that increases prefix pi. Building on our greedy strategy, let's walk through a concrete example. We start with the sequence 1, 2, 3, 6, 4, 5. Since the prefix 1, 2, 3 is already sorted, we focus on the remaining block 6, 4, 5. Which element is smallest? It's 4, so we reverse the segment to bring 4 into the fourth position, giving us 1, 2, 3, 4, 6, 5. Now only 6 and 5 are out of order. Another simple reversal swaps 5 into place, yielding the fully sorted 1, 2, 3, 4, 5, 6, and voila! For any permutation of length n, this greedy reversal procedure completes in, at most, n-1 steps. Continuing from our greedy example, let's see how simple reversal sort can fall short of the optimal number of reversals. For instance, start with the permutation 6, 1, 2, 3, 4, 5, and apply the algorithm step by step. 1. Reverse the first 6 elements. 6, 1, 2, 3, 4, 5. Right pointing arrow. 1, 6, 2, 3, 4, 5. 2. Reverse the first 2 elements. 1, 6, 2, 3, 4, 5. Right pointing arrow. 1, 2, 6, 3, 4, 5. 3. Reverse the first 3 elements. 1, 2, 6, 3, 4, 5. Right pointing arrow. 1, 2, 3, 6, 4, 5. 4. Reverse the first 4 elements. 1, 2, 3, 6, 4, 5. Right pointing arrow. 1, 2, 3, 4, 6, 5. 5. Reverse the first 5 elements. 1, 2, 3, 4, 6, 5. Right pointing arrow. 1, 2, 3, 4, 5, 6. That's 5 reversals in total, even though a single reversal of the entire sequence would have sorted it immediately. This clearly shows that simple reversal sort does not guarantee the fewest possible reversals. Building on our last example with pi equals 6, 1, 2, 3, 4, 5. You don't need 3 reversals. You can sort it in just 2 moves. Step 1. Reverse the entire block 6, 1, 2, 3, 4, 5, yielding 5, 4, 3, 2, 1, 6. Step 2. Reverse the first 5 elements 5, 4, 3, 2, 1 to arrive at 1, 2, 3, 4, 5, 6. Since simple reversal sort would take more than 2 reversals here, this clearly shows it isn't optimal. We therefore need stronger approximation algorithms. To build towards stronger approximation algorithms, we first introduce the notion of a breakpoint in a permutation. A breakpoint occurs between any 2 adjacent entries that are not consecutive integers. For example, consider the permutation pi equals 193478265. We insert vertical bars wherever 2 neighbors differ by more than 1, yielding 193478265. This marks the pairs 1, 9, 9, 3, 4, 7, 8, 2, and 2, 5 as breakpoints. Finally, we denote by b pi the total number of breakpoints in pi. Building on that definition, we now see how breakpoints work in an extended permutation. Start with pi equals 5, 6, 2, 1, 3, 4, then append pi equals 0 at the front and pi equals 7 at the end, giving us the sequence 0, 5, 6, 2, 1, 3, 4, 7. Next, scan each adjacent pair and mark any gap that exceeds 1. In this example, the gaps between 0 and 5, 6 and 2, 1 and 3, and 4 and 7 are all breakpoints. These marked positions show us exactly where the permutation departs from perfect adjacency. Building on our discussion of breakpoints, we extend a permutation by adding two sentinel values, pi equals 0 at the front and pi equals n plus 1 at the end. Let's see this in action with the permutation. 1, 9, 3, 4, 7, 8, 2, 6, 5. When we prepend 0 and append 10, the sequence becomes 0, 1, 9, 3, 4, 7, 8, 2, 6, 5, 10. Notice how this extension introduces a new breakpoint between 5 and 10. By standardizing every permutation with these fixed endpoints, our subsequent breakpoint analyses stay consistent and much easier to handle. Building on our standardized permutations with sentinel endpoints, let's explore how reversals interact with breakpoints. Each reversal can remove at most 2 breakpoints. As a result, the smallest number of reversals needed to sort any permutation, call it OPT, is at least half the number of breakpoints, rounded up. To see this in action, start with the permutation pi augmented by 0 at the front and 7 at the end. 0, 2, 3, 1, 4, 6, 5, 7. This extended sequence has 5 breakpoints. First, reverse the segment from 1 to 4. 0, 1, 3, 2, 4, 6, 5, 7. This move removes 1 breakpoint at the segment's start and 1 at its end, cutting the total to 4. Next, reverse the pair 3, 2. 0, 1, 2, 3, 4, 6, 5, 7. Now we've dropped the count from 4 to 2. Finally, reverse 6, 5. 0, 1, 2, 3, 4, 5, 6, 7. Fide. This last reversal eliminates the remaining 2 breakpoints. In just 3 reversals, we've sorted pi, exactly matching the lower bound of 5 halves equals 3. Building on our previous discussion of breakpoints, let's introduce a simple, yet powerful, lower bound on the number of reversals needed to sort a permutation. First, take pi equals 2, 3, 1, 4, 6, 5, and augment it with a 0 at the front and a 7 at the end. Next, count the breakpoints, adjacent pairs that aren't in increasing order. Here there are 5, so b pi equals 5. Because any single reversal can remove at most 2 breakpoints, the optimal number of reversals must be at least b pi / 2, which is 2.5. So we need at least 3 reversals. In the example shown, we indeed perform 3 reversals. Each step eliminates 1 or 2 breakpoints, and after the third reversal, all breakpoints vanish, yielding the sorted sequence 0, 1, 2, 3, 4, 5, 6, 7. This confirms that sorting pi requires at least 3 reversals, exactly matching our lower bound formula. OPT, reversal distance, is greater than or equal to #breakpoints / 2. Now that we've established our breakpoint-based lower bound, let's look at the pseudocode for breakpoint reversal sort, a straightforward greedy method for sorting by reversals. We start with a permutation pi and compute its breakpoint count b pi. As long as b pi is greater than 0, we examine every possible reversal row and pick the one that drives the breakpoint count down the most, that is, the reversal minimizing b pi ring operator RARHO. We then apply that reversal to pi, update our permutation, and repeat. Once there are no breakpoints left, we output the fully sorted sequence. At the bottom of the slide, you'll see the example configuration 0, 2, 3, 1, 4, 6, 5, 7. Along with the prompt, any problem? That question invites us to ask, does this greedy choice always yield an optimal reversal sequence, or might we sometimes do better? Building on the pseudocode we just saw, this slide walks through breakpoint reversal sort, a straightforward greedy method for sorting a permutation by reversals. We keep track of b pi, the number of breakpoints in our current permutation pi. As long as b pi remains positive, we look at every possible reversal row, pick the one that drives b pi ring operator row down the most, and apply it to update pi. When no breakpoints are left, we've reached a fully sorted permutation and we terminate. Take the example on screen, 01567234889. Here you'll notice that no single reversal can reduce the breakpoint count, which highlights a potential pitfall of relying solely on this greedy strategy. Building on the last slide, let's take a closer look at breakpoint reversal sort, a simple, greedy method for sorting a permutation by reversals. We start with our current permutation pi and keep going as long as its breakpoint count b pi is greater than 0. At each step, we examine every possible reversal row, choose the one that gives the smallest b pi row, and update pi to pi row. We repeat this until no breakpoints remain, at which point we output the sorted permutation. Here's the catch. You'll see it highlighted in red. Even though we always pick the most promising reversal, there's no guarantee that b pi actually decreases every time. In fact, the algorithm can get stuck or even cycle indefinitely, so termination isn't assured. Now, building on our discussion of breakpoints, let's introduce the notion of a strip, any interval between two consecutive breakpoints in a permutation. If the numbers in that interval descend, we call it a decreasing strip. For example, 6-5 or 3-2. If they ascend, it's an increasing strip, like 7-8. In the example at the bottom, we've padded our permutation with 0 at the start and 10 at the end, giving 019437825625610. Reading off the strips, 01 forms an increasing strip, 943 is a decreasing strip, 78 is an increasing strip. 2, as a single element, is treated as a decreasing strip by default. 5-6 is an increasing strip. 10 stands alone as a strip. Identifying these strips is our first step in analyzing the permutation structure. Building on that, let's zero in on the first decreasing run that ends with the smallest possible endpoint, which we'll call k. In our running example, 1465782, we pad with 0 at the front and 9 at the end. In this padded sequence, the smallest endpoint of a decreasing strip is k equals 2. Now take k minus 1, which is 1. You'll notice that 1 lies in an increasing strip. It can't belong to a decreasing run, or else we would have chosen it as our k in the first place. Therefore, 1 marks the termination of its increasing strip. This alternating peel-off of decreasing and increasing strips always picks the smallest available endpoint at each step. Building on our previous discussion, let's start by pinpointing the decreasing strip whose smallest entry we call k. For instance, take the permutation pi equals 1465782, padded with 0 at the front and 9 at the end. Scanning for decreasing runs, we see that the smallest descent endpoint is 2, so here k equals 2. Next, we look at k minus 1, which is 1 in this example. You'll find that 1 sits at the end of an increasing strip, effectively terminating it. Finally, observe how the pair k minus 1 creates 2 new breakpoints, a key feature we'll exploit in the next step. Building on that insight, Theorem 1 tells us that whenever our permutation pi still contains at least one decreasing strip, there's always a reversal row that makes genuine progress. In fact, applying row to pi strictly reduces the total number of breakpoints. Formally, b pi ring operator ri row is strictly less than b pi. In other words, as long as pi has a descending run, we can perform a reversal move that brings us one step closer to the sorted order. Building on Theorem 1, let's examine the permutation pi equals 1465782. To count its breakpoints, we pad it with 0 at the front and 9 at the end, giving 01465783229. Now, we simply tally the adjacent pairs that aren't consecutive integers, and there are 5 of them. so b pi equals 5. The next step is to pick the decreasing strip whose smallest entry k is as small as possible. In our example, that's the strip 3, 2, since its minimum element, k, equals 2. With that strip identified, we're all set to apply the reversal that will reduce the breakpoint count even further. Building on our example with pi equals 1, 4, 6, 5, 7, 8, 3, 2, we first pad it with a 0 at the front and a 9 at the end, giving 0, 1, 4, 6, 5, 7, 8, 3, 2, 9. This makes 5 breakpoints, so b pi equals 5. Notice the two decreasing strips, 6, 5, and 3, 2, and pick the one whose smallest element is as small as possible. In our case, that's the strip ending in 2, so we set k equals 2. Continuing our example, we take the permutation pi equals 1, 4, 6, 5, 7, 8, 3, 2, and pad it with 0 at the start and 9 at the end. Splitting into alternating increasing and decreasing strips gives 0, 1, 4, 6, 5, 7, 8, 3, 2, 9. That's 5 strips in total, so b pi equals 5. Next, we pick the decreasing strip whose smallest element k is as small as possible. Here, k equals 2. Finally, we locate k1, which is 1, in the permutation to continue our procedure. Now that we've pinpointed both k and k1, we're ready for the next step. Now, building on that setup, we start with the augmented permutation. Dot 0, 1, 4, 6, 5, 7, 8, 3, 2, 9, which has 5 breakpoints. First, we identify the decreasing strip, whose smallest element is the overall minimum not yet in place, in this case, 2. Next, we locate its predecessor, 1, elsewhere in the sequence. Then we reverse the entire segment between these two values, the block. 4, 6, 5, 7, 8, 3, 2 flips around to become 2, 3, 8, 7, 5, 6, 4. After reinserting this reversed segment, our new sequence reads 0, 1, 2, 3, 8, 7, 5, 6, 4, 9. That single reversal drops the breakpoint count from 5 down to 4. Clear progress toward a fully sorted order. Building on our last example, let's examine the permutation pi equals 07654328819, which has 4 breakpoints between 0 and 7, 2 and 8, 8 and 1, and 1 and 9. Our goal is to reduce that count. First, we identify the decreasing strip whose smallest element k is minimal. Here, k equals 1. Next, we locate k minus 1, that's 0, in the permutation. Reversing the entire segment from 0 through 1 transforms pi into 0, 1, 8, 2, 3, 4, 5, 6, 7, 9. And just like that, the breakpoint count drops from 4 down to 3. Building on our previous step, let's look at a new twist in our permutation sorting problem. Consider pi equals 0, 1, 5, 6, 7, 2, 3, 4, 8, 9. We break it into its increasing runs. 0, 1, 5, 6, 7, 2, 3, 4, 8, 9. And count 3 breakpoints, so b pi equals 3. Here's the challenge. Every strip is already in increasing order. How do we proceed? Building on that insight, here's a simple 2-step move that always lowers our breakpoint count. First, we reverse an increasing strip. This alone doesn't immediately change b pi, but it turns the strip into a decreasing one. Next, we invoke Theorem 1 to flip this newly formed decreasing strip, and that's what actually reduces the total number of breakpoints. In other words, each cycle of reversing an increasing strip and then its freshly created decreasing counterpart guarantees a net drop in b pi. Building on that 2-step strategy, let's turn to our permutation pi, which currently has 3 breakpoints and no decreasing strips. When we apply the reversal RERS 6, 7, the breakpoint count stays at 3, but crucially, this move creates a brand new decreasing strip. By introducing that descending pair, we guarantee that the very next reversal we choose will reduce the total number of breakpoints. Building on that example, here's an outline of the improved breakpoint reversal sort. We begin with a permutation pi and repeat the following steps, as long as pi still has breakpoints. First, if pi contains a decreasing strip, we examine every possible reversal and pick the one that reduces the breakpoint count the most. If there's no decreasing strip, we instead choose a reversal that flips an increasing strip. We then apply the chosen reversal, update pi, and output the new permutation. This loop continues until all breakpoints are eliminated. So the natural question is, how good is this algorithm? Building on that, we know every reversal can eliminate at most 2 breakpoints. This means any sequence of reversals must use at least half as many moves as there are breakpoints. In other words, the optimal reversal distance is bounded below by the total number of breakpoints divided by 2. Let's see this in action with an example. Take the permutation pi equals 2, 3, 1, 4, 6, 5, padded with 0 at the front and 7 at the end. Initially, there are 5 breakpoints, which we can mark as 0, 2, 3, 1, 4, 6, 5, 7. After our first reversal, flipping the segment from 3 back to 1, the count drops to 4 breakpoints. A second reversal brings it down to 2, and a third reversal clears the last breakpoints entirely, giving us the identity permutation 01, 2, 3, 4, 5, 6, 7. We've used 3 reversals in total, exactly matching our lower bound, 5 breakpoints divided by 2 rounds up to 3. This example shows precisely why OPT, reversal distance, is greater than or equal to number of breakpoints / 2. Building on our breakpoint lower bound, let's now show that improved breakpoint reversal sort is a 4 approximation algorithm for sorting by reversals. The key observation is that in every 2 consecutive reversal steps, the algorithm removes at least 1 breakpoint, so it uses at most 2 bpi steps overall. Call this number of reversals APP. Then we have sequedibur liberal. APP is less than or equal to 2 bpi steps. On the other hand, any optimal sequence must perform at least bpi / 2 reversals overall. OPT is greater than or equal to bpi / 2. Putting these 2 inequalities together gives DIDE. APP / OPT is less than or equal to 2 bpi / bpi / 2 equals 4. In other words, our method never uses more than 4 times the minimum number of reversals. Building on those results, we've developed a 4 approximation algorithm for the unsigned sorting by reversal problem. In other words, for any permutation, our method guarantees a sequence of at most 4 times the minimum number of reversals needed to sort it. The outcome is a provably efficient approach that strikes the right balance between solution quality and computational feasibility for this challenging genome rearrangement task.